Hi everyone, welcome back to the channel Quantum. Before we dive in, if you're interested in learning more about quantum mechanics and other fascinating topics in theoretical physics, please hit the like button and subscribe to the channel so you don't miss any of our future videos. Let's get started. Today, we're diving into one of the most fascinating and foundational concepts in quantum mechanics, the Hilbert space. You've probably heard that quantum mechanics involves wave functions, probabilities, and strange phenomena. But did you know that these all happen within a special kind of space called a Hilbert space? A Hilbert space is where quantum states live, and understanding it is key to grasping the structure and rules of the quantum world. So, let's break it down and discover why this space is so essential. Today, we will also be diving into something equally important: linear operators and their matrix representations. Why do we care about operators in quantum mechanics? Well, operators are how we apply mathematical transformations to states in a Hilbert space. In quantum mechanics, observables like energy, position, and momentum are represented by these operators, and understanding them is key to predicting and measuring properties of quantum systems. But what is a Hilbert space? To start off, a Hilbert space is a kind of vector space, which might sound familiar if you've studied linear algebra. But this isn't just any vector space. A Hilbert space has an additional structure called an inner product, which allows us to measure things like angles and lengths. This inner product also makes it possible to talk about concepts like distance between states or the probability of transitioning from one state to another. In quantum mechanics, we use Hilbert spaces because they provide a mathematical home for quantum states. Think of it this way. If classical physics happens in a three-dimensional space, we can see quantum mechanics happens in a Hilbert space that we can't directly observe, but it's just as real. More precisely, a finite-dimensional Hilbert space is a finite-dimensional complex vector space equipped with an inner product. Let us explain these terms one by one. Vectors in Hilbert space or Dirac notation. In a Hilbert space, we represent quantum states as vectors denoted by ket v. This is called Dirac notation, and it's a compact way of describing quantum states. Each ket represents a possible state the system can be in. Imagine we have a vector space with multiple directions. In a Hilbert space, each direction, or basis vector, represents a fundamental state that our quantum system could take on. We can combine these basis vectors to describe any possible state. This is given in equation 1.1, inner product. Now, let's talk about one of the most important features of a Hilbert space, the inner product. In everyday vector spaces, you might know the dot product, which lets us calculate angles and projections. In a Hilbert space, we have the inner product, which works similarly but can also handle complex numbers. The inner product between two states, say ket v and ket w, is written as the bracket between v and w. This number is fundamental in quantum mechanics because it tells us the overlap between two states, essentially how much one state aligns with another. This concept becomes incredibly powerful when we interpret the result as a probability of transitioning between states. The inner product is formally defined by the linear mapping from v cross v to the set of complex numbers, which satisfy the properties in equation 1.2. The fourth property, positive definiteness, is the most crucial. It tells us that the inner product of any Dirac ket with itself is always positive, and it vanishes if and only if of the vector itself vanishes. The inner product allows us to identify the dual vector space v star of linear functionals from v to the complex numbers with the vector space v itself. Thus, Dirac-Braz, which are the linear functionals, are vectors identified with the Hermitian conjugation of the Dirac kets, as shown in equation 1.3. The inner product property of a Hilbert space will allow us to define the matrix representation of linear operators presented in the next section more explicitly. Orthogonality and normalization. A few more terms that are essential to understanding Hilbert spaces are orthogonality and normalization. If two states ket v and ket w are orthogonal, it means that their inner product, bracket vw, is 0. In physical terms, this often means the states are completely distinct with no overlap. Normalization is about making sure that a state's inner product with itself, bracket vv, is equal to 1. This ensures that probabilities calculated from this state make sense. For example, if a state ket psi isn't normalized, we might end up with probabilities that add up to more than 100%, which doesn't reflect reality. By normalizing our vectors, we ensure that the total probability of all possible outcomes is exactly 1. Basis vectors and completeness. In a finite-dimensional Hilbert space, we can express any vector as a combination of basis vectors. These basis vectors are like building blocks. They're linearly independent, which means none of them can be written as a combination of the others. This concept is essential because it lets us construct any possible quantum state within this space. An interesting process called Gram-Schmidt can turn any set of basis vectors into an orthonormal set, where each basis vector is both normalized and orthogonal to every other. This makes it super easy to work with these vectors because they simplify calculations in quantum mechanics. The Gram-Schmidt orthonormalization is shown in equations 1.5 through 1.10. Furthermore, by means of the outer product defined in equation 1.11, we can derive the completeness relation in equation 1.12. The outer product W times bra V is our first example of a linear operator from the vector space V to the vector space W. This is defined in equation 1.11. The completeness relation derived in equation 1.12 tells us that the orthonormalized basis formed by the Dirac ket's I will span the whole vector space V. This means that any vector in V can be expanded in the ket's I. The completeness relation simply states that the sum of the operators ket I times bra I is the identity operator on the vector space V. As we will see shortly, these operators are projection operators on the Dirac ket's I. But what is a linear operator? To start with the basics, a linear operator is a function that acts on vectors within a Hilbert space to produce new vectors. We denote operators with symbols like A or B. The key feature of a linear operator is that it preserves both addition and scalar multiplication, which means that it is linear, as shown in equation 1.13. This property of linearity is what makes linear operators so useful in quantum mechanics, where they act predictably on states and allow us to build up complex operations from simpler ones. Matrix representation of operators. Now let's talk about how we represent these operators mathematically. In a finite-dimensional Hilbert space, we can represent a linear operator as a matrix. This means that applying an operator to a vector is just matrix multiplication. An explicit example is shown in equation 1.14. In this case, the operator A is literally the M times N matrix M, and it acts from the Hilbert space Cn to the Hilbert space Cm. In general, linear operators can be given a matrix representation, and hence the operator and matrix theories are equivalent, at least in the context of a finite-dimensional complex vector space. Suppose we have a basis set for our Hilbert space, which we'll label as ket v1, ket v2, until ket vn. The action of the operator A on any basis vector vj can be expressed as a linear combination of the other basis vectors. This is shown in equation 1.15. Here, Aij are the elements of the matrix representing A. The element Aij represents the inner product given by the bracket between Vi from one hand and A acting on Vj from the other hand, and gives us a way to understand how the operator transforms one basis vector into another. Matrix representations of linear operators can be made more precise and more explicit by introducing the notion of an inner product. Indeed, by using the completeness relation, we can derive the defining equation 1.15 as shown in equation 1.16. The composition of linear operators will then correspond to the matrix product of their matrix representations as shown in equation 1.17. Eigenvalues and eigenvectors of operators. One of the most powerful tools in understanding operators is through their eigenvalues and eigenvectors. When an operator A acts on a vector ket V and simply scales it rather than rotating or transforming it in any other way, we say that ket V is an eigenvector of A, and the scaling factor lambda is the eigenvalue. Mathematically, this relationship is expressed as in the second line of equation 1.20. These eigenvalues are determined from solving the characteristic polynomial given in the first line of equation 1.20. Once these eigenvalues are determined, we can go back, second line, and solve the eigenvalue problem to determine the corresponding eigenvectors. In quantum mechanics, eigenvalues often represent the possible measurable values of an observable. For instance, if we measure the energy of a system, the result we get corresponds to one of the eigenvalues of the energy operator. Diagonalization and the spectral theorem. For many operators, especially Hermitian operators to be defined below, we can find a basis in which the matrix representation of the operator is diagonal. This is known as diagonalization. When an operator is diagonal in some basis, it means that each of its eigenvalues lies on the diagonal of its matrix representation, making calculations much simpler. According to the spectral theorem, any Hermitian operator can be expressed as a sum of its eigenvalues multiplied by projection operators onto its eigenstates, as given in equation 1.21. Indeed, if the Dirac-Ket Vi is the eigenvector associated with the eigenvalue lambda I, then the operator Ket Vi times Bra Vi is precisely the projection operator on the state Ket Vi. This spectral decomposition is particularly helpful because it allows us to break down complex operators into simple parts related to their eigenvalues and eigenvectors. In general, the spectral decomposition theorem states that any operator A is diagonalizable, i.e., it admits a spectral decomposition given by equation 1.21 if and only if A is a normal operator, i.e., A dagger times A is equal to A times A dagger. This is shown in equation 1.22. The Hermitian conjugate of the operator A, namely A dagger, which is also called the adjoint of A, is defined by equations 1.3 and 1.24. Clearly, in the matrix basis, we simply take the transpose followed by the complex conjugation. For a Hermitian operator, the Hermitian conjugate is equal to the operator itself. Two Hermitian operators A and B are commuting, i.e. their commutator, which is equal to A times B minus B times A, is zero if and only if they are simultaneously diagonalizable, i.e. if and only if there exists an orthonormal basis in which the two operators are diagonal. This fundamental theorem is shown in equation 1.27. Naturally, a basis which is an eigenbasis for two or more operators is a preferred basis. This is because commuting Hermitian operators correspond to physical observables which can be measured simultaneously. Hermitian, unitary, and projection operators. Not all operators are created equal, and in quantum mechanics, certain types of operators are particularly important. Hermitian operators. An operator A is Hermitian if it's equal to its own conjugate transpose, meaning a dagger equal A. Hermitian operators are essential because their eigenvalues are always real, making them perfect for representing measurable quantities like energy or position. See equation 1.26. Projection operators. A projection operator P has the property that P squared equal P. This means that once you apply the operator, applying it again doesn't change the outcome. Projection operators are useful for extracting certain components of a state, like measuring whether a system is in a specific state or not. See equation 1.28. Unitary operators. Unitary operators preserve the inner product between vectors, which essentially means they preserve the length and angle of vectors. If U is unitary, it satisfies U dagger times U equal U times U dagger equal I, where I is the identity operator. Unitary operators are crucial for describing time evolution in quantum mechanics because they ensure that probabilities remain consistent over time. Furthermore, unitary transformations represent similarity transformations which change basis vectors and linear operators. The eigenvalues of a linear operator, and hence the trace and the determinant of that operator, are invariant under similarity transformations, and thus they are invariant under the action of unitary operators. See equations 1.29, 1.30, and 1.31. The trace of an operator, which is the sum of its diagonal elements, gives us useful information in quantum mechanics. For instance, the trace of a density matrix, which represents a quantum state, is always equal to 1. The determinant of an operator is another useful property, often related to whether an operator is invertible. For example, unitary operators, which are common in quantum mechanics, have determinants with an absolute value of 1. Why matrix representation matters. So why does representing operators as matrices matter? The matrix representation makes it much easier to perform operations like addition, multiplication, and taking powers of operators. It also simplifies complex calculations, allowing us to compute things like eigenvalues, traces, and determinants, which are all important in understanding physical properties in quantum mechanics. So to wrap things up, the Hilbert space is where the magic of quantum mechanics unfolds. It's a complete, complex vector space equipped with an inner product that lets us calculate probabilities and describe quantum states in ways we can't with classical physics. Hilbert spaces might sound abstract, but they're essential for describing the reality of quantum systems. They give us a structured framework for understanding superpositions, measurements, and the bizarre nature of quantum mechanics. Furthermore, linear operators and their matrix representations are vital tools in quantum mechanics. They give us a structured way to work with observables, describe transformations, and compute measurable properties in quantum systems. From Hermitian operators that correspond to real, measurable quantities, to unitary operators that describe time evolution, operators are the language of quantum mechanics. Thanks for watching, and I hope you enjoyed this exploration of Hilbert space. If you found this video helpful, please like, subscribe, and let me know in the comments what quantum concepts you'd like to see next. See you in the next video.